Hello, so this is a recording on chapter 5. Now some of you have already taken the exam. That's your choice. That's why I gave you the opportunity to do it early. That you can move at your own pace. That's the beauty of being on the internet. And I think any course that's asynchronous, you should be able to move at your own pace. So, but for those of you who haven't, let's go over chapter 5. But we should be doing this anyway, right? So again, everything you need is in this textbook. Now, this is an interesting situation because many people tend to not want to do work on their own. You want us, the professors, to, feed it to you, just like hand feed everything to you. One thing I've learned early in life is that if you have that attitude, you're going nowhere. You have to be your own boss, your own change agent. If you depend on other people to do stuff for you, you're never going to succeed in life. Never. Unless you're like royalty where you get people servants. But there is no such person like that I know of. So what we do instead is we have to make our own lives and forge our own paths, figure things out for ourselves. When you're in the work world, you're going to be asked to figure things out for yourself all the time. And if you can't do that, it's not on us, it's on you. You're the one who's failing in that case. So you have to use this opportunity to do so. I'm the perfect professor for that because you can talk to me about anything. If you're worried about something, just tell me. There's always a way through everything because my goal is to make you better human beings. Let's look at this chapter really quickly here. So when we get into hypothesis testing, and again, I'm relying on you to read this. When we're getting to hypothesis testing, we want to know if our sample somehow is representative of a population. We always start with some kind of a population and we make assumptions about the population. And we want to see if our sample is different. Like, for instance, we find a sample of really, really tall people. And we want to know, are these people part of the population? Or are they a unique population that we'd never even knew of? Like, did we just discover a new population of people who are really, really tall? That's what hypothesis testing is all about. So we always have some population, and this is a normal distribution. It's that bell-shaped curve. So most of the people are here centered around 0. This is actually a standard normal distribution with a mean of 0 and a standard deviation of 1. You see this hump here? This represents a count of individuals at that level, right? So most of the individuals are here, fewer individuals are here, and fewer individuals are here. Now, the important thing is that you can have samples of people from every part of this population, and this is what these little samples represent. Some of them are closer to the mean, some of them are further from the mean. The ones that are further from the mean, we assume that they belong to a different population. But that's not an accurate assumption. You should always assume that they belong to this population unless you have proof that they don't. And that's what hypothesis testing is about. We always start with the assumption that our sample comes from the population, and the alternative is that it doesn't come from the population. Now this, I'm not going to go over all this stuff here, but just except for to say the standard error is the standard deviation of the sampling distribution. So each of these samples has a mean, and we take these means from these samples and we distribute them, right? We just do a regular, like say we treat each sample as a unit, right? And if we were to plot these samples, we'd get this normal distribution of means, and the mean of all those sample means would be the population mean. Remember, the mean of the sample means is the population mean. The standard deviation is what we call the standard error of the mean. This is just a sigma, which is standard deviation for the population, because this is a Greek letter, divided by the square root of the sample size. So that's the standard error. Sorry. Now, in terms of margins of errors and confidence intervals, you'll see confidence intervals very often in statistics. Confidence intervals are basically, in a nutshell, I like these in a nutshell. I've never looked inside a nutshell except for to find nuts. But in a nutshell, we'd say that how confident are we that the sample belongs to the population? That's all we're asking, right? How confident are we that the sample belongs to the population? And we usually set that value at some defined level, like say 95%. We want to be 95% confident, etc. And when we compute that confidence interval, we have to calculate something known as a margin of error. So if I have a good one of these here, we have to compute a margin of error. And that margin of error is some area around our mean value. Let me see if I have a good picture of a margin of error. Yeah, here it is, right? So when we calculate our confidence interval, it's a confidence interval for our mean value. So that's why you'll see the x is, it's not a mu, so it's not a Greek letter, so this is a sample, right? It's a confidence interval around the sample because we want to know whether the sample belongs to that population. And the margin of error, we're using this this nice normal distribution, so we're converting everything, we're standardizing it so that we can use the normal distribution. Although you'll see later that we can do this with a t-distribution as well. It's z1 minus alpha over 2 times the standard error. So we have to calculate our standard error, and then we have to know what the z value is. This looks like mystery to you, right? What the heck is he doing? Well, you know, alpha is our probability of a type 1 error. Usually it's 0.05, right? But it doesn't have to be 0.05, and that's important to know. But we divide it by 2 because we are splitting our population or our sample in half, right? Because some are above the mean and some are below the mean. The confidence interval surrounds the mean. So we have to split this alpha in 2, split our uncertainty in 2, and we subtract from that from 1. So, you know, we're going to find a z value that's associated with this confidence limit. And we already did z values in the last chapter. We saw how we can convert these z values into probabilities. Okay, so that's what we're doing here. So we're finding the z value. So like for instance, this could be, you know, the confidence interval surrounding the mean. Let's see. I explain everything here. You just have to read it. I explain in complete detail how I do this, even with my inane examples, right, from my institute. So here I show you what's an alternative hypothesis. We generally write the null hypothesis as h sub 0, and the alternative is h sub 1. Right, so I can make this alternative hypothesis whatever I want it to be. I could say that it's, you know, greater than the mean, less than the mean, equal to the mean. I could do whatever I want from it. Okay, so now I present this table here to show what happens when we make decisions. Yeah, so this is what happens if we reject. So the null hypothesis is the hypothesis we would like to reject. So we always start with the belief that there is no effect. So like for instance, if I'm testing a new drug to see if a drug will treat the coronavirus and cure the coronavirus, I assume that it doesn't work. That's how science works. We always assume that we're wrong, and then we have to find evidence that we're right. If you're watching the sad incidents that happened yesterday in the Capitol building, there are a lot of people who have these obscure conspiracy theories, and they're acting upon it because they're believing them without any evidence for them. So in science, we don't do that. That's why you won't see good scientists protesting like that, because a good scientist will look for evidence that disconfirms her hypothesis. And then once she can finally ignore all of that evidence, or dismiss all of that evidence, all of those disconfirming pieces of evidence, then she can finally say, oh, my idea is right. And that's what we do in science, right? So, but we can make 4 different types of decisions. We can reject the null hypothesis when the null hypothesis is true. That's a false positive result. That's called alpha. So this is what that alpha represents. We can reject the null hypothesis when the null hypothesis is false. That's what we want, and we call that power. We have power. You'll notice I have 1 minus beta because these two are complementary events. We can accept the null hypothesis. Some people will say fail to reject. Okay, so that's okay. I don't care which one you, as long as you understand what the essence of this is. We can accept the null hypothesis when the null hypothesis is true. That's confidence. Or we can accept the null hypothesis when the null hypothesis is false, and that's what we call a type 2 error. So type 2 error and type 2 error, 1 error are different. You have to know these four. These are very important, not just for this exam, but for all exams. So let's see what I want. So we just make a decision to reject a null hypothesis if we have enough evidence to say that the result that we obtain is highly unlikely given that the null hypothesis is true. So let's assume this is the null hypothesis population. If we find a result that has a probability of occurring that's very, very small, it's very, very small. So this represents 5% of the distribution, right? This little segment here represents 5% of the distribution. If we say, if we find our sample mean, remember that figure I showed with all the little sample distributions? If our sample mean's out here, that means it has less than a 5% chance of occurring if the null hypothesis is true. Notice that I said if the null hypothesis is true. And that's going to be on the test, actually. The p-value is the probability of the observed result given the null hypothesis is true. So if you have a probability of your observed result that's less than or equal to 5%, this is saying that, okay, this sample could actually belong to the null population. But in reality, it probably doesn't. It has like a 3-4% chance of occurring if the null hypothesis is true. So it's more likely that it doesn't belong to the null population. Now, why do we select alpha? Because we can be wrong, right? We can have a false positive result. Like I can say that, I can make a conclusion that my sample does not belong to this population when it actually does. Because again, you can be part of this null population and be at one of the extremes, one of these tails right here. Like you could have like a 3% chance of being a part of the population, but you still belong to the population. You're just an outlier. Then I would be wrong in making my decision. I would have committed a type 1 error. But there's less than a 5% chance of me doing that because my value is so extreme. So when we select our alpha, we're selecting an acceptable level of being wrong. So I can accept a 5% or less chance of being wrong. So okay, I'm wrong, but the probability of me being wrong is very, very low in that case. That's the essence of hypothesis testing. Okay, so now the next thing we're doing is we're conducting these tests. We're comparing our samples to our population. So we collect sample data, we get means for these samples, we get standard deviation, well, we get means and standard deviations for these samples, and we want to make a comparison to the population. We want to make a comparison to the population. Let me see where here it is. We want to make a comparison to the population. So like say my sample has a mean of 70 and a standard deviation of 30. If I know the population standard deviation, like say again, like if I was doing comparing a sample on the math SAT score to the population, I have the population mean and standard deviation. And the standardized test, people collect all the scores and they have the population values of everybody who ever took them. So in that case, they do have the standard deviation. So if I'm comparing my sample to the population, this is the equation I would use to calculate my z-test score. This is my z-test score, right? It's mean, sample mean minus the population mean. So it could be negative or it could be positive, divided by the standard error, right? But notice I have a sigma here. If I don't have the population standard deviation, I can use the sample standard deviation as an estimate of my population standard deviation. This is what we call a t-test. T-distribution and a standard normal distribution are almost the same. In fact, if we let n approach infinity, and when I say n approach infinity, I mean it gets larger and larger and larger, sample size, the two are indistinguishable. So the t becomes the z. So these are just calculations of this. Let's see. This is n33. Is this using? Let me just make sure I'm using the z value. Oh yeah. Okay. Oh no. So I'm doing a t-test here, but it's all the same. Okay. But let me just show you what I did here. So this is my null hypothesis. I always write down my null hypothesis first, and then I write down my alternative. Now you'll notice that this is one directional versus two directional. Because I could have said mean is not equal to 50. Okay. you're gambling here. Statistics has a lot to do with gambling. We're gambling, and we're saying, I bet that, okay, that if I'm right, my sample mean is going to be greater than the population mean. Now, I could have taken a cop-out approach and said, well, I think that, yes, I think the null hypothesis is wrong, but I'm not really sure whether my mean will be larger than or smaller than the population mean. So I could just say these are not equal. There's a price to be paid for being a statistical coward. I call it a statistical coward, but it's not really cowardice, because in some cases it makes sense to do what we call two-tail versus one-tail. This is considered a one-tail test because we're only moving in one direction. We're looking at, is the mean greater than the population mean? Is the sample mean greater than the population mean? You have more power. That means you're better able to reject a false null hypothesis if you use a one-directional versus a two-directional test. Whether we use the t or the z distribution here, the process is exactly the same. So here I am, I calculate this value. Well, this is a z value, right? So let's see. So difference is 20 for whatever this. I'm not even looking at what this example is. I can't remember. We have the standard deviation divided by the square root of the sample size, and we get 3.830. I know this is significant, just off the top of my head, because I know what the critical value is for an alpha of 0.05 one-tailed. So you need to read how to differentiate a one-tail test from a two-tail test. I mean, I give you like all this nice stuff here. I even show you what would happen if it was negative. You have to understand that this distribution is symmetrical. It's symmetrical. Well, here's an example of two-tailed. Say I said mean is equal to 50, mean is not equal to 50. The only difference there is that because I'm doing oh, this is awesome stuff. Sorry, I love it. I loved writing this textbook. The difference here, so this shows you the difference, and this is so fundamental and so important to this course that I need you to dial this down. This is going to be more important than anything else you learn in this whole course, probably. How to interpret these p-values and critical values and stuff like that. If my alpha is 0.05 and I select a one-directional test, I'm looking at either the upper 5% or the lower 5% of the distribution. Got it? So if I'm using a one-tail test, I've got all this area from here to infinity to reject the null hypothesis. So notice how I'm closer to the mean, right? At z, so this is the z value associated with a one-tail test, 0.05. Notice how much closer I am to the mean than if I do a two-tail test. So that means values that are closer to the mean can actually reject the null hypothesis. That's power, right? I don't have to have such a large value. My calculated z value would have to just be equal to or above 1.645 to reject the null hypothesis with a one-tail test. If, on the other hand, I take the cop-out approach and do a two-tail test, now I have to split my uncertainty, because either I could be wrong, but I could be wrong above the mean, or I could be wrong below the mean. So I take that 0.05 and divide it into 2. So I have the upper 2.5. This is 0.025. If I multiply by 100, that's 2.5. This is the upper 2.5% of the distribution. This is the lower 2.5% of the distribution. So now I've got to find a new z value. The z value associated with this is 1.964, or it could be negative 1.964. It's symmetrical. It's exactly just like folding two pages, or folding, a page in half. Notice how my z value, this is called the critical value, how my critical value, z critical value, got larger. So now in order to reject a false null hypothesis, my calculated z value has to be larger than 1.964. I lose power. For those of you who are interested in a career that involves research, know that I could always increase my power, my ability to reject a false null hypothesis, by doing a one-tail instead of a two-tail test. Got it? I could also change my alpha to 0.10. What if I change it to 0.10? And now my two-tail z value would actually be 1.645. Could be 5% here and 5% there. So a lot of the tricks that we can do. Read this and get to know it. It'll be your friend. Let's see what else. You can read it. I explain everything there. So when we calculated our z-value, I think we got 3 point something, right? It was 3 minus 3.830. If this is a two-tail test, it would reject it because it's above negative 1.964. If it's a one-tail test, it would reject it too because it would be above minus 1.64. So in either way, it rejects it. Make sure you understand this stuff. Study, and remember, I have an office hour today at noon.